Okay, folks, it's the apparently red eye edition of my stream. Uh, I don't know if you'll see the actual time on my computer, but it is currently 3:45 in the morning, and I should really be sleeping, but couldn't sleep. So hey, what? Let's go stream, right? So here we go. Let's see what is live. What is live? Just kidding. All right. Let's do this. Um, ooh, what's this? I'm doxing numbers. I don't know what those are for, but anyway, and I'm also doxing my setup. All right, this is a microphone. This thing here. Anyway, all right. Behind the scenes look at the shadows. All right, so here we go. Um, we are going to do um, yeah, we're gonna work with about 5 to 10, probably six if I'm not counting incorrectly, series today. And then we're going to do contest math problems. Fun stuff. So, all of these series could by themselves be slightly tweaked to become a contest math problem, but they are not. Okay, so let's just get started. So, the first series that I have on my list is good old 1/2 plus a fourth plus an eighth plus 1 over 16, yada, yada, yada. Okay. Without going into a lot of detail, this is a geometric series. It's an infinite geometric series, and its sum is 1. So whatever you see all of this written down, you can replace it with this. That is the definition of an equal sign. You see one side, you replace it with the other side. It's that simple. All right, cool. Second series. Um, oh, it's just like, it's running around. 0.1 plus 0.01 plus 0.001 plus 0.0001. And oops, dot dot dot. That is equal to 1/9. Why is it equal to 1/9? Because you add these two together, you get 0.11. You add the next one, you get 0.111. You add the next one, you get 0.1111. And for those of you who are well initiated with repeating decimals, know that those of you, yeah, okay, no, checking my grammar, know that the sum is 0.11111111, and that is equal to 1/9. So there we go. That is the second series. All right, so the next one. It's called the harmonic series. Again, these are all infinite series. This series doesn't converge. It doesn't get you an answer. Don't pass go. Don't collect 200. Collect infinity if you want to, but not 200. This series doesn't work. It turns out that if you group these series elements into 2s here, and then into 4s here, and then into 8s here, you get a half plus more than a half plus more than a half plus more than a half. If you add a bunch of a halves, that doesn't give you any number. And if you add a bunch of a halves, if you add a bunch of more than halves, again, no number. So this one is bad. Can't do that one. Okay. There's one more infinite series I want to talk about. Actually, this one will be finite, probably. Yeah, let's just call it a finite series. All right, so 1 over 2 plus 1 over 6 plus 1 over 12 plus 1 over 20 plus dot 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 to 1 over, let's say, 9900. Yeah. we can calculate this. We can make it something. It turns out that when you have a finite number of these, it definitely converges because you can't add a finite number of numbers and have it not be bounded or, whatever, converge. But the point here is that we have 1 minus a half plus a half minus, a third, plus a third minus a fourth, dot, 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 dot. And this last one happens to be, let's see. I want to say 1 over 99 minus 100. Sorry, 1 over 99 minus 1 over 100. Let's try that. So this is what we call a telescoping sequence, or series, sorry. We're going to get rid of these guys because it's minus a half plus a half. Gives you 0. Most of the time when you try to add a half to a negative half, gets you 0, gets you 0. Okay, so finally we have 1 here minus 1 over 100. That's 99 over 100. And that's how you simplify that one. Okay. So, nothing really surprising, nothing stunning, I guess you could say. Maybe I've lost my love of numbers, interested in other things, who knows. Well, let's keep going. And there's one more I want to kind of point out. This one is just equal to 50, 50. 5,050. All right. So, if you didn't know what this one added up to, it's equal to 5,050. That's all you need to know. I don't want to get into that one. Okay. So, how is this all related to contest math? Well, one simple thing you can do. Oops, let's see. Where is the thing? Let's move this way. Oops. I can't seem to deal with paper today. All right, here we go. Perfect. Okay, so one thing that they can do with series is just to take the whole series and multiply by something. So I'm going to pick a random series on this side. Actually, preferably something with fractions. Ooh, actually, this one's really nice. This one's, well, nah. Okay. Let's just pick the first one. Okay, so they can take the whole series, and if you multiply by a finite number, you get like the left side being the series and the right side being the 1 times the finite number. Okay, so for example, pi. Pi's a nice one. Pi over 2. Good old 90 degrees for those of you who know radians. Plus pi over 4, plus pi over 8, plus pi over 16, yada yada yada. What does that equal? Well, it turns out that the left side is pi times, sorry, it turns out the left side is pi times the left side of this. So another way to write this is pi times 1/2 plus a 4th plus an 8th plus a 16th. I sure hope I'm starting to write all this correctly. Which is equal to pi times 1. Why is what 1? We see the left side here is also here. So this is equal to 1 because it says on our paper. Duh. Okay, cool. So pi times this equals pi times that. So the answer here is pi. That's it. End of story. End of story. So you can take a constant and multiply by any of these series, and then you'll get the rest of the series after you factor the constant out, and then you just multiply by the right side. So not a big deal, really. So that's the first thing that can happen. The second thing that can happen, which is the more crafty way contest math problems usually do these, is they hide the addition as something else. Okay, so what does that mean? Well, we have these things called exponents. And, what's a good one? What is a good one? Okay. Yeah, for example, we have exponents. So what do we get when we have 2 times 2 squared times 2 cubed times 2 to the 4th, dot, 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 2 to the 100th? If you know your rules of exponents, you take all the exponents, if it's all the same base, which in this case it is, and you just add up all the exponents. So the left side simplifies to the right side. Now you might look at the right side and say, well, there's a part of it that looks very, 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 very familiar. Namely, this one here. Can you see that? Yeah, okay. 1 plus 2 plus 3 plus 4 plus 5 plus 6, dot, 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 to 100. That equals 50-50. So this answer here is just 2 to the 50-50. If the contest problem creator were a little more crafty, they could have done 2 to the 1/5 times 2 to the 2/5 times 2 to the 3/5, yada yada yada, 2 to the 20th. Okay, it's actually the same problem pretty much. Oops, maybe I should box this away because that's a different problem. But yeah, so this is equal to the 1 plus 2 plus 3 plus 4 dot 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 100 to the 1/5. And in this case, we would get 2 to the 50-50 to the 1/5, which is equal to 2 to the 1010. So 2 to the laugh out loud out. Yeah, something like that. Anyway, the point here is that with some manipulation, you can make the series seem less visible, and you can add extra steps to the end to make the question harder to answer. So there you go. All right. Now we have some examples with square roots. Okay, so I didn't know if I was going to do logs today. I kind of don't want to, because, well, maybe we might do one log problem, but I think square roots and exponents are fair game. So let's try. Yeah, let's try 2 more problems, and then we'll see what the time brings, and if anybody else has a question. If you have a math question or have a math comment, please state so. It would be nice. But here we go. Here's question 1 of 2. Square root of 3 times square root of 3. Physics and depression, how are you doing? Enjoying sandwiches. Okay. That's funny. I have... Actually, is he here? He's not there. Sure, go ahead. This is like dot 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 here. I don't know if you can see it, but yeah, it goes on forever. Have fun. You don't need to stab the sandwiches. I'm kidding. Bad jokes. X squared over 3 equals X. That might be true. Might be true. Oh, I see what you're doing with this. Okay, that works. Yeah, okay. So what do you get for X? Just making sure. Yeah, X equals 3. Okay, okay. So you're probably doing this kind of thing. but that's x instead for your equations. Okay, well, so you can square both sides, which is what you did, I think, and it's not wrong, but you technically have to show that it actually converges. But okay. So for our purposes, we have, if I can find the paper, we have 6 series that we kind of know, and we have the answers to. So the first one is half, fourth, eighth, 16th. That's equal to 1. Okay, fine. 0.1, 0.01, 0.001, 0.0001. Okay, so then you got point. So we had the first two, you get 0.11. Add another term, 0.111. Add another term, 0.1111. You have a bunch of ones repeating after the decimal point. That is 1/9, and therefore that series goes to that. Okay. We have this series, which is the harmonic series, which is not convergent at all. Not in the infinite sense, anyway. So if you keep adding things like this, 1/2, 1/3, 1/4, 1/5, you will not get anything, because by grouping them, you can show that it's bigger than 1/2 plus 1/2 plus 1/2 plus 1/2 an infinite number of times. And since we know that 1/2 plus 1/2 plus 1/2 already goes to infinity, anything more than that will probably go to infinity too. All right, so that's the third one. Quick review. Sorry, you probably don't need this. But anyway, so the next one is a telescoping sequence, or series, sorry. You got a half, you got a sixth. So this is 1 times 2, 2 times 3, 3 times 4, 4 times 5. And if you have a finite number of terms, namely, we're just going to stop at 1/9900. I'm just going to say that the first one is 1 minus a half, the second one's a half minus a third, the third one's a third minus a fourth. And I wrote down all these nice things in parentheses, and guess what? 1/2 minus a half is 0, 1/3 minus a third is 0, 1/4 minus a fourth is 0. Okay, so they all cancel except for this last term of -1/100. So you get 99/100. And the last wonderful series from 1 to 100 added together is 50/50, and that's a whole nother simple thing. Okay, so the trick is to make this problem have a series that looks like one of these guys. Like, this is super watered down. I mean, this one could have been 1/3 plus 1/9 plus 1/27 plus 1/81st, but the point is that, like, you find a nice series in the problem that you have. So, okay. So let's simplify. This is 3 to the half. This is 3 to the half, a fourth. 3 to the 1/8. 3 to the 1/16. Dot, 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 dot. Okay, cool. And now, exponents. Perfect. Great. So when we multiply things together with the same base, we have the exponents. So it's 3 to the half, plus a fourth, plus an eighth, plus 16th, dot, 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 dot. Okay, so then we can see a nice series here that we recognize, and we end up getting 3 to the first, which is 3. And there you go. Using what you know that looks complicated to simplify something that is no longer complicated. Yeah, no logarithms. Right. Yeah, that's so okay. So the deal here is it's not going to be difficult. There's some really nice contest problems with series and summations and logarithms, but I kind of wanted to, like, not go too crazy this time. Okay, so this is problem number 1. Okay, cool. So the next problem, problem number 1 with roots. The next problem with roots. Here we go. Logarithms. All right, let's see. Where are the things that I wrote down? Give me, like, literally 10 seconds, I hope. Where are my... Wait, I just had it. Where'd it go? Okay, maybe more than 10 seconds, but hold on. It's in this pile, I'm pretty sure. No, not that one. Okay, here it goes. Okay. I'm trying to check what order I wrote something in, and I just want to make sure that I, like, do the same thing here, otherwise I'll get confused. All right, so cube root of square root of 6 times fourth root of cube root of 6 times fifth root of fourth root of 6 times dot 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 dot. Okay, until we get to, I don't know. How about 100th root of 99th root of 6? And the question is, what's going on here? Don't use logarithms, please. Okay. So yeah, so that's the problem. We have our list of things to use here. Which one should we use and why? So you're trying to get the problem to look like one of these. I mean, I don't have to explain this to you. You know what you're doing probably, or at least you know definitely the basics. So what do we do here? What do we do? Last one. This one? Wait, which one do you mean by last one? Because, like, it was off the page. So, yeah. Second to last. Okay, yes. Totally. Cool. Okay. How do you know to use that, though? Like, how do you make this... How do you rewrite this to, like... I know I'm being picky here. How do you rewrite this to make it look exactly like this? Okay. Let's use a wonderful thing. It's the newest technology that I know of. Papers had it for millions of years or something. Okay, maybe like thousands, but still. It's called folding. Let's try that. Okay, so. Okay. Fair enough. All right. So we have cube root of square root here. And that just means it is 6 to the 1/6. The next one is 6 to the fourth root, third root, 1 over 12. Next one is 6 to the 1 over 20. Dot, 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 dot. 6 to the 1 over... Oops. Yeah. Yeah. Okay, I almost confused myself. 9,900. And that almost looks like this one here. We're missing a 6 to the 1/2, which I probably should have included, now that I think about it. But okay. 6, we can add 0 and make it look nice. So 6 to the negative 1/2, plus 1/2, plus a 1/6, plus a 12th, plus 1 over 20, dot, 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 plus 1 over 9,900. Okay. And, yeah, we got good stuff here. So this is equal to 6 to the negative 1/2 plus 99 over 100. And that is, that leaves a square on the right side, which is kind of nice. But anyway, square on the top and the bottom of the fraction. 49 over 100. And that is the answer. We're good here. Wow. I have taken up a whole like 20 minutes. This is supposed to last an hour. Kidding. All right. Well, it was supposed to last an hour, but I think we're just going to end this if there's no questions. Do you have any other questions, Mr. Physics and Depression? Neat. I'm trying to think if there's anything. Yeah, 6 to the 7 over 10 squared. Yeah. It's good stuff. What can I show you that will just... What can I show you that'll just like drive you crazy? Like, that's kind of cool. All right. Let me think. I can put up something that I already put up last time when you weren't here. But I'm trying to think if there's anything kind of cool and new that. Oh, okay. Well, how are you with number theory? Yeah, I saw what you were doing. That was complicated. Yeah. Okay. Number theory is terrible. Okay, okay. Oh, here's a fun one. Well, this one isn't so bad. I think you. No, okay, okay. Oh, let's do a locker problem. You might have you ever heard of the locker problem, where you start out with like 1,000 lockers and then you do stuff to them and try to figure out how many lockers are open or closed at the end. Like here, just give me a topic and I'll try my best to humor you. I'm not sure if I know enough about every topic, but kind of give me sort of a general thing. Does that ring a bell? Okay. Um, hmm. Well, we could just do like normal kind of brain teaser problems. So let's just do sports related brain teaser problems. Fun stuff. Um, if you have 1,000. Okay, okay. Well, let's do this one first. Let's warm up. Okay. You have 1,000 chess players, and they're playing 1 minute games. And the tournament is single elimination. And the question is, how many games have to be played until you get to a winner? Don't know if you've heard this one yet, but anyway, we'll do the locker problem after this. So yeah, you got 1,000 people in a tournament. It's single elimination, and each round they kind of pair up as best they can. Yeah, it's 999. Okay, good, 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 good. All right, it's a nice classic one. Single elimination means every time someone loses, um, they get thrown out. So there have to be 999 losses before everyone is thrown out except the winner. So yeah, okay. The locker one. All right, here we go. Here we go. Here we go. So we've got lockers, 1,000 of them. Dot, 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 dot. All right, so they're numbered. One. Not computer science. They start with one. The last one's 1,000. Okay, so there's a very bored student, of course, and he decides he's going to go to all the lockers and open all of them, every single one. Opens all the lockers. Okay. So after the first step, all of these lockers are open. Dot, 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 open. Okay. O is for open. P. No, not P. O is for open, and C is for closed. So the next deal is he goes back to the beginning and closes every even numbered locker. Okay, so that's after the second run through. On the third run through, he alternates every locker, or every third locker, starting with three. So this one was open. It is now closed. And this one doesn't change because it is not a multiple of three. Okay, so yeah. And he keeps doing this until he gets to 1,000 steps. And the question is, how many lockers are open at the end? You can take more than a minute. You don't have to do this like. Okay. Anyway, yeah, sure. This is also a really nice, sort of classic problem. Okay, and I know the answer, but let me just write it down before I like forget due to stress. Okay, okay. Now you're making me hungry. Just like, okay. And I have one more cool problem after this one, um, and it has to do with boxes. Uh, so before we continue, I want to know how much backseating you want from me. Yeah. So I don't mind the sort of text and thinking, but it's gonna be hard for me to you know keep quiet because I'm that kind of idiot. Yeah, boxes. Okay. How do you figure out if either of those statements are correct? Okay. I'll happily draw if you want me to. Okay. Sure. Okay. Okay. So tell me more. Okay. 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 Um. Okay. So. Okay. Okay. Fair. Yes. Still wondering how many are open, but okay. I like the thought. I like the process is good. Yeah. Okay. Well, that's that's the problem. You gotta answer that thing. Sorry. Yeah. Okay. Um. Couple things I want to add to the sort of enrichment of the problem. Not directly dealing with the problem, but just other things I wanted to say. Yes, 31 squared is 961. That is correct. Okay. What is 2 to the 20th? Do you know how to. Do you happen to have that number in your head? Clearly, I'm asking without a calculator, but just wondering. Okay. Yeah. Yeah. How'd you get that? Just wondering. Did you use 2 to the 10th? Yeah. Oh, nice. Nice. Okay. Yep. Okay, cool. All right. So that's the first aside. The second aside is 31 squared is like 13 squared but backwards, which is kind of a nice thing. Um, because when you're doing the expansion of 3x plus 1 or 1 plus 3x, oh no, I messed up. 3x plus 1 or x plus 3 squared. Either way, the terms don't carry or borrow. Yeah, yeah, okay. Good, good. All right, cool. Um, Anything else I wanted to say about this? But yes, that's the squares, and 31 is the correct answer. You get you get locker number one. No. Okay, so kind of like two more things. I want to talk about the bin problem, and then or the box problem, and then I want to end with kind of cool stuff that's like actually on the cutting edge of research ish. All right, so here we go. So we got a bunch of bins or boxes. It doesn't matter. Okay, so we have a bunch of them. Let's say we have like 30. Okay, so here's the pattern. Not going to be fun. The first pattern is you take the leftmost bin. and you have these things. You have these spheres or balls, and you want to put one ball in the leftmost bin. Okay. I like how you're getting excited about like kind of like quadratic expansion. It's cool. No, I get excited about it too. It's good. All right. So anyway, um, all right. So step one, we have one ball in the leftmost bin. Oh man, 2 to the 13th is just 2 to the 10th times 8. Sorry, I I didn't mean to like say anything about that, but there you go. Okay, sorry. Um, okay, so yeah, step one, you have you have a ball in the leftmost bin. Oh, 30th. Oh, I thought it was the 13th. Sorry. So 2 to the 30th would be 1024 cubed, which is one of those x cubed plus 3x squared plus 3x plus 1 type things. So, or sorry, x cubed plus 3x squared y plus 3xy squared plus y cubed things. Yes, okay. I don't happen to remember what 24 cubed is, but it's something. But that's cool. I like it. I like it. Okay. But yeah, okay, so the first step's this, okay? Yeah, well, okay, so the first one is a 1. The next one is a 72. The next one is a, ouch. Yeah, okay, the next one's difficult. It's like 576 times 3, and the next one's 576 times 24, so yeah, alright. Cool, cool. No, good, good. Yes, okay. Alright. So anyway, step one, you put something in the leftmost bin. Step two. Okay, so this is the entirety of step two. There is more than one part to step two. Step two is you put another ball in the leftmost bin. Then, every time you have a bin with two balls, you take both of them out and you put. I'm trying not to like. I'm trying to make the calculus kids feel bad. I'm kidding. I'm kidding. No. But anyway, so you take these two out, and you end up putting one in here, and these two go away. In the third step, you put a ball in the leftmost bin, and nothing happens because there are no bins with two balls. Okay. In the fourth step, you put another ball in the leftmost bin, but unfortunately there's two balls in this bin, so you take them both out. Put another ball in this bin, but guess what? This bin has now two balls, so you take them both out, and you end up with that. I understand there are fourth graders that can do these problems. Don't. But anyway, all right. So yeah. So the question is like, what year is this? This year? Is it a good year? Yeah, I guess we can do that. So this year is 2023. How many of these boxes have a ball at the end of the 2023rd step? And that's the problem. How are you doing, Mr. Chief Cohomology? This is not. I don't think this one's obvious. Like once you get it, it's like, well, okay, but it's not like the discovery is not easy. And yeah. Okay, well just for simplicity, um tell me about the 1000 first step. I gotta make sure I can do this one too. Okay. Oh, I can just do that. That'll be easier. Um, ah. Um, for 1001. Let me just use the calculator thing because I don't want to give the wrong answer. Like that's more important than the pride of doing it like by hand. All right, let's see. Oh, oops. Yeah, it's yeah, it's not 5. Okay, let me write down the number of things just before. So we're doing this one. Are you doing this one or that one? That's important. That's very important. Which one are you doing? 2023 or 1001? Let's see what 2023 gives us. No, okay, so yeah, this one is not 5. The 1001 one is not 5, yeah. I'm cheating. Yeah, streamer's prerogative. Okay. Yeah, it's not 8 either. Um, okay, so okay, what would you like me to do? Would you like to rethink your logic or just sort of have me sort of, like tell me what to do basically, yeah. Or comment on stuff that you've thought or, whatever. Well, just yeah. That is correct. That is correct. How'd you get this one? And while you're doing that, I am going to check to make sure that I did the math right on the site that I used. Why can't I type? Yeah, okay. Yeah. Okay. Yeah, that isn't quite right either. Although I like the logic. You might want to know that 1023 has 10 digits. Okay. Yeah. Just like 1 has 1 digit and 3 has 2. Are you okay? Okay, yes, it's 7. All right, all right. So, I'm going to try to go through a little number theory. Um, Fun stuff, really. Okay. Um, yeah, so 2040. Oops, I can't write zeros apparently. 2047 has how many? 11? Yeah, 11. 11 ones. And then you have to subtract enough to get rid of some ones. So, 24. 24, 16 plus 8. So there's two ones. So, yeah. So, 9 ones. Yeah, yeah. Nice. Yes. Okay. Um, Man, I don't know if I want to tell you about all this stuff. There's something that I don't know if you'll like. High five, indeed, indeed, high five. Um, Tell me, do you want to learn some number theory today? And the second thing is, okay, okay, all right, good, good, okay. So there's a function we call rad in number theory, and rad is the product of the distinct prime factors. So 13 times 11, rad of that is just 143. It's 13 times 11 because they're both prime. Okay. Rad of a prime number, let's say 101, which happens to be prime, by the way, yeah, is 101. Now, what gets really interesting is if a number has a lot of prime factors that are the same, like 72. 72 only has twos and threes. Yes, yes, I am slightly familiar with that. Both, yeah, because I think I've watched your streams, so yes, I happen to know a little bit about it, but not this particular week's, if that's what you're asking. And by the way, not to like downplay recreational math, but this is not recreational math. This is serious stuff. People are studying this kind of stuff like now. Um, okay, so, uh, yeah, we're good with this. Rad of 13 times 11, 143, because they're both primes. So we just take the prime factors of 13 times 11 and we multiply them out. Okay, okay. Yeah, this is accessible, but definitely cutting edge math. Okay, yeah, all right, all right. So, rad of a prime number is just itself. No surprise there. The prime number only has one prime factor itself, and you multiply it out, you get that. Rad of 72 is 6. 72 only has twos and threes, therefore the rad of it is 6. Okay, so uh, rad of like, let's say, uh, eight one. Oh, let's not make it too big. 8100 is just threes, twos, and fives. So that would be 30. Okay. So here's the deal. There's like a, without getting into too much detail, there's a conjecture that has, I think it still hasn't been proven, but there's a conjecture that is hard to prove if you can find certain triples of numbers with a particular property. Okay, so triples of numbers, like Pythagorean triples, but not in this case one of the ones that we want. But like, just saying, there's three of them. Okay, triples. Okay, so what you want with the triple is you have a triple ABC. This has to satisfy two conditions. Condition one, A plus B equals C. Actually, no. Oh, it has to satisfy a few conditions, but okay. Um, yeah, let's put the zero condition. Sorry. A, B, and C can't share any factors. All right, so this can't be like 2 and 8 and like 7 because 2 and 8 share a factor. Okay. So I already messed up big time. But anyway, okay, so A, B, and C, they don't share factors. They're what we call coprime, I think. Yeah. Anyway, A plus B equals C, and 2, rad of A, B, C is less than C. Alright. So this is like cutting edge research. If you can find triples of this kind, then, well, sorry, if you can find certain types of triples of this kind, then it makes the conjecture hard to prove or impossible to prove or something like that. It's these are related to the conjecture somehow, and I'm not going to get into that because that's just, yeah. So the first question is, can you think of one? Like, can you find two numbers that add to a third number where the rad of the product of all three is less than the largest one? Sorry. And A, B, and C have to be positive integers, or just whole numbers, basically. Okay, yeah, yeah. Not so easy. Not so easy. Not so easy. Yeah. Okay. So there's only, I believe, there's only three or four triples where all three numbers are less than 100. So yeah, kind of cool stuff. And I'm gonna try to figure what they are because I don't think I remember actually. By the way, one can be one of the numbers. Just sort of saying that. Oh, and I think they have to be distinct. So yeah, so that's another thing. You can't put 111, or well, 111 doesn't work, but you know what I mean. All right, let's not go there. I think that might, I'm gonna incriminate myself somehow. Okay, so that's another one. Yeah, okay, I found three. Hopefully, there's no more because if there are, I can't find them. Oh, maybe that's another one. No. Hmm. Oh. There's another one, I think. No, not that one. That's not one of them. Hmm. Yeah. Um. All right. So, would you like one of them, just to kind of get a feel for what's going on here? Okay. Do you want the lowest one, or do you want the middle one, or the highest one that I can find right now? I've forgotten how to do this actually, so it could be a problem. But anyway. Wait, no, there is one more. I think. Yeah, I think that might be one of them. No, no, it's not. All right, whatever. All right, okay. All right, middle. Okay, middle is that one. Okay, 1, 63, 64. I hope this one works because it's been years since I've checked this stuff. So yeah. All right. So here's a 1, 63, 64. Uh, we agree that 1 plus 63, 64. That's not that bad. So requirement 2. The primes that go into these have to be multiplied together and less than 64. Is that true? Well, the primes are 3, 2, and 7, right? So this one has 3s and 7s. This one only has 2s. So when you multiply them together, you get 42. 42 is indeed less than 64. And yeah, so that's one of them. There's one above that and one below that, ish. So that's it actually has direct consequences. Okay, if the conjecture is proven true, the story is that Fermat's last theorem is proved in a page. So, if the ABC conjecture is true, it's so powerful that Fermat's last theorem can be proved in a page after it. Um, yeah, yeah. You can go look it up. It's called the ABC conjecture. It has its own web page by a French university, and I assume it's a French mathematician. But anyway, ABC conjecture. There's a dash there too. Um. So yeah. So I was fiddling around with this, and I found not just infinitely many, but infinitely many of a sort of very general pattern. Okay, so let's try that one. 1, 15, and 16. So I don't think that's going to work because 15 is 3 times 5, and 16 is a 2, and 3 times 5 times 2 is already 30. So, yeah. Yeah, yeah. Okay, so anyway, um, this was part of a single lecture in the like colloquium lecture series at this university I was at, and the guy who went there to speak to us was from Berkeley, number 30 guy, and he was like, "We really need to find these triples. Like, we really need to find them, but we have really no way of finding a lot of them. So we're just gonna do it randomly." So he was, and this is like almost verbatim what he said. He said, "Go take your phone number and subtract, your credit card number, and then see if it forms an ABC triple." I mean, he was kidding, obviously, but he was like, "There's no good way to find these," and blah blah. And so yeah, so that was the problem given to us in the colloquium. Um, just go find some license plates and subtract some what do you call it, barcode numbers, and then see if it forms an ABC triple. He was really gung ho about trying to find these things. But anyway, so yeah, so it turns out there's infinitely many. Yeah, that I mean, would that be great? Like you're just like standing in line at Walmart, and you're like, hey, like to the person in front of you, you're like, hey, can I see your credit card number? I need to find this certain type of mathematical structure, and I need your credit card number for it. Like, sorry, it's just yeah. I should be more serious. This is a serious conjecture. Um, but anyway, yeah. So yeah. It turns out, and I think I can say this because like the people know about this already. Um, I kind of posted it on Reddit. But anyway, yeah. It turns out there's infinitely many triples of the form 1, 2 to the n, 3 to the m. And there's also infinitely many triples of the form 1, 3 to the x, 2 to the y, where this one's the bigger one. And, like, I can keep going. Like, there's a bunch of form, like, it actually ends up being true that 1, p to the, let's say, k, q to the r. There's always, like, infinitely many of these guys. The problem is there's this thing in the ABC world called quality. And as far as I know, the quality of these guys is not necessarily good. So there's like qualifications that certain triples will have a bigger impact on whether or not this thing can be proved. So yeah, so that's kind of the way it is. In fact, like technically this can be an A also. Like there's lots of things you can do with this, but the point is that like there's a lot of triples in a lot of different forms. Um, I am. Let's see. Yeah, let's. Well, anyway, yeah. So there's that. There's that. I was very happy with this Reddit post that I made because there were people who were like, actually, this is pretty cool, and the upvote percentage was actually pretty high. So I was like, cool, I'm good. But anyway, so that's a little bit of what's been going on in the number three world. Yeah, find really good triples. Figure out what those mean and find some good ones. Yeah. That's my ABC triples presentation today. um, so open-ended question. There you go. Heritage would be proud. Have you watched his documentary? Oh, it's a good one. Yeah, he has a. I think it's called "The Man Who Loved Only Numbers," or maybe that's the book. There's a book and a movie, and the movie might be called "N is for a number" or something to that effect. I've forgotten. You can look it up. Or actually, no. What am I doing? I'm boss here. We can look it up on Google. Uh, Heritage documentary. N is a number. There you go. Okay, so let's write it down. N is a number. Yeah. There's also a Ramanujan film. I now say Ramanujan because that's the way they pronounce it in the film. But yeah, the Ramanujan film is called "The Man Who Knew Infinity," and it's a good one too. Yeah. Um, yeah. So thank you for. Well, do you have any other questions? Let's see if I can entertain something else. Oh, yeah, that's supposed to be really good. Um, yeah, the documentary's good too. Okay. Uh oh. So what is it? What is it? Uh, I have no idea. Is it like Is the Earth exactly 1 radian around the sun from January 1st? I mean, I don't know. Is it really? I'm just guessing. If that's true, okay. We'll start a rumor. Start a rumor within math circles, literally circles. That's funny. But yeah, and we'll talk about how Pi Day. That's actually a good question. Like Pi Day, it's actually exactly 1 radian away from what days of the year? Oh, does it spell like? Does do the numbers turn out to be like 999 or 314 or something? That would be funny too. Like, never mind. I don't know. I'm just guessing randomly. Like if you do the is it called the Caesar cipher? I forget what it's called now. But anyway, have you heard about Old MacDonald? And he had a farm. Old MacDonald had a farm. Negative 2i. All right. I think these cheesy math tips at the end of stream are gonna like scare away everybody else that wants to watch the stream later. Like subsequent episodes. Really? Well, that's not supposed to happen. But okay. Uh, I think I'm gonna like end stream. Is that okay? It's 5 in the morning. Also, I should, you know, I should refresh too. But like, sleep wise. All right. Thanks for coming, man. Always entertaining. I'll see you here at my stream, or there at your stream soon. I'm sure. All right. Thanks, and I'll see you guys later. Oh, Old McDonald. E minus I, and you get never. Okay, fine. All right. Bye.